right, well, let's go ahead and get started by reviewing some things. I told you in our last lesson that we would have a quiz over section 11.3, quiz over machines, our simple machines. And Audrey, what are the 6 simple machines?
The lever, the wedge, the pulley, the inclined plane, wheel and axle, and
the one that you turn it and it goes up and down.
yeah,
That one.
and this one,
The screw. All right. So we're just about had all 6 of them there. And with these simple machines, what is the purpose of a machine?
To multiply work, to increase work. I don't know. I know, but I don't.
Not to increase it, but to
make it easy.
make work easier. There we go. Now, how do machines generally make work easier, Michael?
They multiply force.
They multiply force, right? But they multiply force at the expense of distance. Or in some cases, they can multiply distance at the expense of force. But generally speaking, we think of machines as multiplying force for us. In fact, we refer to the ability of a machine to multiply force as mechanical advantage. There we go. So mechanical advantage, the ability of a machine to multiply force. We talked about 2 types of mechanical advantage. One type, Audrey,
The ideal mechanical advantage.
the ideal mechanical advantage. In general, how did we find IMA for our machines?
Distance input over distance output.
Good. Input distance over output distance. And then, Michael, how do we find what's the other mechanical advantage?
Actual mechanical advantage.
Actual mechanical advantage, and that was found?
Force output over force input.
Okay, the output force over the input force. And again, for the different machines, we might have defined these different ways. Let's start with the first simple machine that we had discussed, and that was the lever. And we said a couple things about a lever. First of all, we need to assume that a lever is inflexible. And the way that a lever functions is at some point on the lever, it has to pivot. Right? So it's a long, inflexible object that can pivot. What do we call the pivot point of the lever, class? The fulcrum. And then there's the purpose of the lever, obviously, is you are using the lever to try to move something. And so the thing that is being moved is called the
load.
The load, okay? And of course, the fulcrum, or excuse me, the lever is going to put out force at the load. You're going to put in force, well, the input force, but some texts will refer to it as the
effort.
Effort. I don't believe that's a term you have to know for this class, but the effort is where we put in the force. And depending on the style of the lever, the design of the lever, usually the idea is that the lever will make your work easier by multiplying your force. Now, in some cases, the lever will actually multiply your speed, depending on which side of the lever and the design of the lever and that kind of thing. For the lever specifically, we had, first of all, an equation we called the law of levers. Audrey, what was that equation?
F sub I times R sub I equals F sub O times R sub O.
There we go. The amount of force that has to be put in, or the effort, times the length of the, what do we call this R sub I, class? Well, R is chosen for radius, but we actually on a lever don't call it the radius, because it doesn't make a full circle. Called the lever arm. Remember, that's the distance from the fulcrum to wherever the effort is applied. That's the input lever arm. And of course, you have the output force, and then this, of course, would be the output lever arm. So the product of the force and the lever arm is equal in both senses. The other way we could look at this was we said that for a lever, since we are assuming inflexibility, and since we're assuming inflexibility, and since we're assuming no friction, we said that for a lever, AMA and IMA are going to be equal, which means that pho over phi has to equal di over do, will also equal pi over rho. And because we said that for a lever, the IMA could be written input lever arm over output lever arm, because the distances will be proportional to the lengths of those lever arms. So We had AMA here, IMA, both of these could have worked for the lever. So if we're finding a lever's IMA, I would usually go with lever arm ratio versus distance ratio. AMA, just output over input. That's the lever. Now we said there's 3 different classifications of levers based on their design. Most levers we typically think of as class 1 levers. What's the key to a class 1 lever?
The fulcrum's in the middle.
Fulcrum's in the middle. And by middle, by the way, it doesn't necessarily have to be like the midpoint or the center per se. Though on our lab on Thursday, we're going to do some different tests with a meter-long lever. And if you balance the lever at the middle, everything's good. The math works great. If you balance the lever anywhere else, you can still do it, but the numbers aren't going to work properly because the mass of the lever will start to affect things. If the mass is balanced at the center, it's fine. But by middle, it just means it's in between, right? For instance, we said the wrecking bar, right? The pivot point is way down at one end, which gives you a very small output lever arm and a very long input lever arm. But the fulcrum doesn't have to be at the very middle. It just has to be in the center. I said a good example to think of, though, for a class 1 lever would be
Seesaw.
the seesaw. Good example, because you're not going to picture a seesaw any other way than fulcrum in the middle. We said a class 2 lever. What's in the middle?
The output force.
The output force or the load, and I said a good example is the wheelbarrow, where it pivots at the wheel. You hold one end lifting up, which is the input force, and the load is there in the middle. And then the class 3 lever, what's in the middle?
Input.
The input, the one that ain't been used yet, right? And a good example I said would be baseball bat. And the key to remember there is that the pivoting happens at the wrist while the hands actually put in the force. Now I said a class 3 lever is the one that will always multiply speed, right? The key to speed, I mean, if you wanted to swing your arm around to try to hit a ball, number one, you'd hurt your hand. But I mean, you could, I suppose, but if you can add that much more distance, you can move the bat head around much faster, and you can even move your hands around. And so you're able to multiply speed. Class 2 lever, I said, always multiplies force. Class 1 could really go either way, but assuming you put your force in on the longer lever arm, you're going to multiply force, right? As long as the input lever arm is the longer one, you're going to multiply force. But if you were to apply force on the shorter lever arm, then you'd be multiplying speed. You'd have to put in more force. From there, we talked about the inclined plane, aka ramp, right? We said for a ramp, the purpose, of course, is that you don't have to lift the object. Instead, you can simply roll it or slide. You're pushing it, right? You're pushing instead of lifting. The ramp does the lifting. So we said for the actual mechanical advantage, it is output force over input force. But I said, how do we define the output force of a ramp? What force does a ramp put out since a ramp lifts? The force of weight. Whatever the weight of the object is, that's what the ramp is taking care of. You are putting in force that we usually have referred to in the past as the applied force. Generally speaking, to what two forces does the applied force equal if there's no acceleration? Friction and weight in the x. Now, if there is no friction or negligible friction, it's just the weight in the x. But generally equal to those two things. Now, again, if you're accelerating, that won't be the case. But typically speaking, when an object is being pushed up a ramp, you're just trying to keep it moving at a steady rate as opposed to actually speeding it up. And then for the IMA, again, it's not that IMA has changed. It's still input distance over output distance, but the way we think of input distance for a ramp has changed. How do we think of input distance? The length of the ramp, right? However long the ramp is from base to end, and then the output distance of a ramp, since a ramp lifts, the change in the height. However, we said that for a ramp, if the change in height is here and the length is here, we said those are both related to the angle of inclination of the ramp. And so we said another way to find IMA is to base it off of the angle of the ramp. What was that formula? Good, the reciprocal of the sine of theta. Again, not new problem here, just, again, same things, just redefined a little bit. And of course, the free body diagram is going to be the key on any type of ramp problem. As far as a wedge, I said a wedge is designed to do one of two things, class. Split or cut, right? Cut or split. So any type of blade you can think of as a wedge. I mean, a doorstop, I guess you could think of as a wedge as well. Though a wedge is more of an inclined plane, I suppose. I said for our definition of a wedge, thinking of it as a machine designed to accomplish a task like cutting or splitting, we'll think of a wedge as two inclined planes back to back, right? Two inclined planes back to back. And I said the key to more efficient wedge, a more effective wedge, is to make the blade of the cutting device or splitting device thinner and deeper, right? Thinner and deeper. So a really, really short blade isn't going to accomplish nearly as much as a really thick or deep blade, I should say. And so that knife, that butcher knife or whatever, can cut through things much more easily and efficiently than the little steak knife. That's designed to cut like this, not chomp, okay? And of course, the thinner it is, the deeper it is, the more efficient the blade will be. More effective, I should say. Efficient's a different word. Let's see, from there we moved on to the screw. And thinking of the screw not as the fastener, but as like a screw jack. And the purpose then of the screw jack is to lift something while you simply turn a handle, spin around a handle, right? You turn a handle and it does all the lifting. You just turn around something. Round and round and round and round and round and round and round. And one little jack lifts up in the air. And if there were no friction, the car would come tumbling back down, but there is friction. Which means that the ideal mechanical advantage in AMA, you like that, thank you. Appreciate that, Audrey. Michael's like, anyway. So the jack, again, you turn it round and round and round, and it lifts little bitty bits at a time. The idea then of a screw in its design is really all it is an inclined plane that's been wrapped around a rod, right? So you've got this rod or thin, small cylinder, narrow cylinder with an inclined plane wrapped around it. Now, the wrap can be a really tight wrap or a really pronounced wrap. Like here, for instance, we have a rather tight wrap, and then in places there is a less tight wrap. You know, it had been pointed out to me that this wrap is not perfectly even throughout, but in a screw it must be, right? There must be a continual angle of inclination of that ramp, if you will, as it goes around the rod. And but if you were to look at just a cross section, you see a distance between where those ridges are, and that distance between the ridges is called pitch. And so as you make a turn of the screw jack handle, it lifts one pitch for every turn that you make. AMA is still going to be output force over input force. And again, assuming you are lifting something, the weight will be the output force, just as it is for a ramp, because after all, a screw is an inclined plane wrapped around a rod. You're also putting in a specific amount of force or applying a certain amount of force. Whatever force you apply or whatever force you put in would go underneath the output or the weight. But we said for a screw, the IMA can be defined a little bit differently. It is still output force over input force, but, it is still defined, the IMA as input distance over output distance. But I said that the key to the jack is as you turn the handle one time, it goes up one pitch. Or if you're lowering it, as it goes backward one turn, it goes downward one pitch. So the input distance is a complete turn of the handle. How can we show a complete turn of the handle? 2 pi r is going to be the circumference of some circle, where r is simply the radius of the circle you're making with your hand. Assuming your hand is at the end of the handle, the length of the handle would be the radius. And then the output distance for the screw jack is the pitch for every one turn of the handle. So there was what we talked about with the screw. From there we talked about a pulley, and I said you can think of a pulley as a circular lever, right? But instead of just tilting like this, though you could have something roll back and forth, it just keeps turning, so you have infinite spin amount on that lever. And the purpose then, if you think about it though, a pulley wheel, whatever the input lever arm is of one side is going to be the same as the output lever arm. So if the lever arms are equal, a single pulley doesn't have any IMA, does it? Or any AMA. So I said a single fixed pulley on its own is Think of it as a circular lever that's used to,
Multiply, no.
it doesn't multiply anything. All it does is
Change the direction.
change the direction, redirect your force. Instead of having to pick up something, you're pulling down on a rope or cable or whatever it is, and that's redirecting your force. But I said if we used, for instance, a single movable pulley, fix the pulley not to, for instance, the ceiling, but fix the pulley to the object, and then anchor one end of the cable to the ceiling. Well, now as you lift, you're going to be lifting a lot more cable than the object moves up. As you pull on the cable, it only moves up half that distance, right? Which means for every 1 foot you want, or centimeter, you want the box to rise, you have to pull twice as much. And if you're putting in twice as much distance, you should be getting out twice as much force if there were no friction, right? Now again, there's going to be a little bit of friction, but minimal friction, right? So I said you can get an IMA for a pulley, you can get mechanical advantage from a pulley, but you need at least one pulley to be movable. You could put lots of pulleys in combination, lots of different wheels all together. And if you have a number of different pulley wheels all being used together, we call that combination a
Block and tackle.
block and tackle. There we go. Think football. After last night, I don't want to think football. It was actually a really good game through 3 quarters. I mean, through 3 quarters, we were playing solid football. I mean, within a 2-point conversion of tying it up, we were playing good game. And then the 4th quarter happened. Almost pick it off, but we didn't. And then they get a touchdown. Interception, touchdown. Fumble, touchdown. Fumble, touchdown. Interception, touchdown. And it was a 2-point game turned into, 54 minus 19, 35-point game. It's very bad. Very bad. All right. Anyway. Anyway, block and tackle. That one, yeah. Block and tackle. Kendall's like, I'm just glad I'm not a Colts fan. All right. Thanks, Kendall. We're praying for you, too. All right, block and tackle. And so it said the key to a block and tackle, figuring out the AMA, you would actually have to somehow get a measurement for how much force was applied, how much weight was lifted up, right? So it'd still kind of be a weight over applied force type thing or an output over input force thing. But for the IMA, how did we calculate it? There wasn't really an equation. What was the key to calculating IMA for a block and tackle, Michael?
The number of ropes.
Well, I mean, it's all one rope, but
The number of ropes across the middle.
yeah. So if you look at the cable winding around and around and around the pulleys, you would have to count how many different strands of cable are. Again, it's one continuous cable. It's got to be. But if you count it across, kind of a cross section of the cable, and again, we'll see this Thursday, how many strands are there? But specifically, not just how many strands are there, but how many strands are doing what? Going up. How many strands are lifting? Now, all the strands lift, except the free strand, the end strand that you're actually pulling. If you're pulling it down, does that count? No, because that's not lifting. All the other strands are lifting, but that one strand isn't. However, if the free strand is coming off a movable pulley and you're pulling up with it, then the free strand counts. So the key is how many strands are lifting the load. All of them plus the free strand if it's a movable pulley you're lifting up. All of the strands except the free strand if it's a downward coming strand off the fixed pulley from the top. So yeah, you have to have a picture in order to calculate IMA for a pulley. So if I'm industrious and I actually give you a picture, then you would count them up. And if I'm lazy and I don't give you a picture, then you don't have to worry about the IMA of a pulley. It all depends on how lazy your physics teacher is. See? All right, then the last simple machine we talked about right at the end of the hour on Friday, it would have been for us, was the wheel and axle. And I said the key to a wheel and axle actually being a machine is that the wheels have to be different sizes, and of course they must connect. Ideally, we think of them as being on the same axle, but it's not always true. Now, for a bicycle wheel, remember we said there's all those gears on the side of the rear wheel, right? Well, those gears are connected on the same axle to that wheel. But then you've got the wheel of the pedals that are turning a gear that turn the other gear. So they're all connected together, but the key is that you have these wheels connected to each other. And again, differing size is what actually makes it a machine in that sense. Otherwise, it's just a pair of wheels that are rolling downhill. For the wheel and axle, then again, we said however much force you get out divided by how much force you put in. That's the AMA. No real change there. The IMA, though, we said the distance you put in is turning one of the wheels. And as you turn one of the wheels, because they're connected, the other wheel must turn also. Correct? So if we're thinking d sub I over d sub O, turning a wheel, as we even commented with the screw, turning something, class, is going to be a circumference, or 2 pi r. But in this case, both distances will be 2 pi r. So what's going to happen to the 2 and the 2's and the pi's?
They cancel.
So for our purpose, we said the same equation that we said we could use for lever arms, we could use for the radii of the wheels, input radius over output radius. And that will give you the IMA of the wheel and axle. Questions on those 6 simple machines? Now, we said IMA and AMA, unless we're dealing with a lever where we have to assume inflexibility, they're not going to be the same as each other, right? The ideal will always be greater because perfect world scenarios always work out better than real world scenarios. But what we'd like to do is have the AMA as close as possible to the IMA, right? We'd like them to be very similar numbers to each other. That makes a machine work better. It means the machine is working at its optimum level, as ideally as possible, as efficiently as possible, right? So we said to find efficiency, which we said is going to be represented by the Greek letter eta, we said perhaps the easiest way to find efficiency, since we do so much with AMA and IMA, is to simply make a ratio of, but we said efficiency is always expressed as a percent. So if we multiply by 1 or 100%, it'll give us a percent unit for our efficiency. That's not actually the definition, but that's an easy way to find efficiency, assuming you found AMA and IMA already. What's the definition of efficiency, though? Audrey, do you remember?
Work output over work input times 100%.
Good. It's actually defined as the ratio of output work to input work expressed as a percent. Well, again, it doesn't multiply work. It multiplies force, but it doesn't multiply work. In fact, you lose work because of energy losses through the use of the machine. So however much work it puts out compared to the amount of work you put in. If it puts out, like we assume for the lever, if it puts out all the work you put in, then it's 100% efficient. No machine's perfect. So you'll never get out more than you'll put in. In fact, you'll almost always get out less work than you put in. But that ratio as a percent is efficiency. Questions on that before we look at the homework handout? All right, well, let's go and take a look at the handout then and see how we did here. Go and read the first problem from the handout for us, if you would, Michael.
A 47-pound boy sits at one end of a 12-foot long seesaw. Another boy sits 2 feet from the other end to balance. And how heavy is the second boy?
All right, so one of the things I hope you did was, did you draw a picture? I love pictures. So here is a seesaw. There's the pivot point. And the seesaw, it says, is a 12-foot long seesaw. And one boy, that's the boy, very fat, weighs 47 pounds. The other boy, we don't know. But I don't put him at the end because it says he sits 2 feet from the end. So he slides forward 2 feet, and there's the other boy. And we don't know how much he weighs. Now, what I'm going to use here, since it's a seesaw, we know, class, which machine is that? The lever. And for the lever, we typically use the law of levers equation, right? So the law of levers equation is phi re over pho rho, or phi ri over pho rho, depending on whether we're going with the, anyway. F sub I, R sub A equals F sub R sub O. And if we look at the first boy as the input, doesn't really matter which one we do, but if we think of him as the input, class, his force, of course, is 47 pounds, and his input lever arm, 6 feet, right? 6 feet on either side. And then the output force, I don't know. I don't know how much force the other kid weighs or his output force. But I do know his lever arm is 4 feet, right? 2 feet forward, but the whole lever arm would have been 6. That leaves a lever arm of 4 feet. And so we multiply, we divide, and we end up getting the other boy is 70.5, or I think it's 2 sig figs. Yes, rounded off to
71 pounds.
71 pounds for the other boy. Did we get that answer? All right.
I just overthought it.
Overthought it. Okay. Question? All right, let's go on to the next one. And Audrey, read the next problem for us.
A man uses a 1.25 meter long rod to try to pry up a fence post. He places a brick 0.45 meters from the end of the rod and exerts a force of 315 newtons at the other end. How much force will the rod exert on the fence post?
All right. So once again, I would draw a picture. This is the fence post. That is the lever. That is the brick. Okay? And it says the rod is 1.25 meters, which I guess is about like my 4-foot wrecking bar. That's a little over 4 feet, but it's about the length of my wrecking bar that I used at home. And he says he places the brick 0.45 meters from the end of the rod. So that right there is 0.45 meters, class. We would call that the output lever arm. By the way, if it's 0.45 meters, what's the input lever arm?
0.8.
0.8 meters. All right, and it says he pushes down on his end with a force of 315 newtons. And the question is, how much force lifts up on that fence post? So once again, we need to use the law of levers equation. There we go. We need to use the law of levers equation. And let's see, F sub I would be the 315 newtons he puts in times his lever arm 0.8 meters. And the output force is what we're finding. Output lever arm 0.45 meters. We multiply, we divide, we end up getting how much output force on the rod or on the fence post. Yeah, I don't know if it came out evenly to 560. That's what I have here. 560 newtons, which is already 2 sig figs, which is what I needed. So 560 newtons is what I had also. Question?
I wrote out everything right. I don't know why I don't have the right answer.
Plug it into the calculator again. Make sure it's not a calculator issue or calculator usage issue. You got it now? Very strange, very strange. Okay, questions on the second problem? All right, let's go on to the next problem. And go and read it for us, Michael.
A man slides a 13-kilogram box up an 8-meter long ramp to the roof of a 4-meter tall building. If the coefficient of friction is 0.27, find the force the man must exert, the AMA, the IMA, and the efficiency of the ramp.
Okay, so 13 kilograms really isn't that bad anyway, but he's sliding it for some reason. So we have a building, that's a building, and it is 4 meters tall. He uses a ramp that is 8 meters long. We have a box that's 13 kilograms, and we know the coefficient of friction is 0.27. There's one number that's not given to me here that's really important with any ramp.
Angle.
The angle. There's no angle given to me. Well, I can find the angle because I know that the opposite is 4 meters. And I know that the hypotenuse is 8 meters. Opposite, hypotenuse, which trig function? Sine. And I know that the sine of an angle is opposite over hypotenuse, or 1 to 2, we could reduce it down. But how do I find the angle theta? Take the arc sine. So if we take the arc sine of a half, we'll get it, though you two being in trig, you should have already known what the arc sine of a half is. 30 degrees. So we have a 30-degree angle for this ramp. Now, I'm actually going to jump to part 3 first. So there's 4 answers we're looking for. I'm going to jump to part 3 because it wanted to know the IMA. And how do I find the IMA for a ramp?
Distance,
1
no,
over something.
Either 1 over sine theta or
length over height.
length over height. Well, it told me the length and the height. So
2.
8 over 4 is 2. IMA of 2, and if we go 2 sig figs, we'll say 2.0. So there's your IMA. So we can go and get that out of the way early. Again, you could take the reciprocal of the sine of 30, but it would come to 2 anyway. Easier just to look at the 8 over 4. You know, I'm just going to push this out of the way. That worked well the other day. We'll just do that. It's out of the way. Okay. Let's see. First thing it said was find the force the man must exert. But to figure out the force that the man has to exert, to find his applied force, we got to find a lot of other numbers first. For instance, we need to find the weight, which acts
Downward.
straight downward. And then what am I going to have to do with this weight?
Split it into that.
Split it into a weight in the y and weight in the x. Now, the only reason I actually need the weight in the y is to get the normal force, and the reason I need normal is to get, and if there is no friction, I don't even need to worry about it, but there is friction. So I do need to worry about it. And again, these are the two right here that I'm really concerned about, the weight in the x and that friction force, because that's what the applied force is going to be equal to. Again, assuming a constant speed up the ramp. It doesn't mention an acceleration. So first things first, I need to find the weight of the box. And what do we get for the weight class?
27.4.
And then we'll use, I'll go with the weight in the x first. We just get it into memory. We'll multiply that by the sine of 30 to get, actually comes out evenly for the weight in the x. I think you were looking at the y, 63.7 newtons. And actually I don't need a memory for that because it came out evenly. I'll use the cosine to get the weight in the y, which is, Michael,
110.3.
blah, blah, blah. And that's also going to be the normal force then. And I'll multiply that by 0.27 to get the friction force, Audrey.
34.
Just get the 110.3, blah, blah, blah.
Yeah.
Multiply by 0.27.
29.7.
Yeah, 29.78, blah, blah, blah. All right, now, these two forces are what the applied force is working against. So we just add them. We take what's on the calculator still with Audrey, and we add the 63.7. How much force must he apply? 93.48, blah, blah, blah. Rounding off to 2 sig figs, we'll say he has to apply 93 newtons of force to push this box up the ramp. All right, sounds like Michael got the 93. Audrey, no. Does it make sense now? All right, did you get the angle?
Yeah.
Okay, so you found the 30-degree angle. I was like, let's say if you miss the angle, you're kind of stuck on how to do anything else. So I had to get that angle first. The next part says find the AMA. Of the ramp. And how do I find the AMA for a ramp class? Output over input force, right? How much force does the ramp put out? It lifts 127.4 newtons. How much force does the man put in? So if you put this in the memory of your calculator, it turns out this is the first time I've actually needed it. I can take the 127.4 divided by the memory value. What do we get for the AMA?
1.36.
And 1.362, blah, 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 rounded 1.42 sig figs. And we said the IMA we already said was going to be 2. So if we want to know the efficiency of the ramp, the easiest way to find the efficiency is to divide the AMA, which is still on the calculator, the 1.362, by the IMA, which is just 2. And we get what for the efficiency?
68%.
0.681, blah, 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 but rounded to 2 sig figs and making it a percent, move the decimal twice, we do get, Audrey, you just said it,
68%.
68% efficiency. Questions on ramp problems. Again, we did a lot with them in chapter 9. Questions as we revisit them here in chapter 11. All right, and then the last problem that we had was the screw. Go and read that problem for us. Go back to Audrey.
A screw jack has a handle that is 12 inches long and a thread pitch of 0.18 inches. If a man can lift a 2,500-pound car by turning the handle with only 65 pounds of force, find the AMA, the IMA, and the efficiency of the jack.
All right. Let's see here. It says, first of all, to find the AMA. How do I find AMA? Always.
Force and no output of it.
Yeah.
Output over input force, right? Now, output force is how much the screw jack lifts, which is 2,500 pounds. A little over a 1-ton car, or 1 1/4 ton, I guess. And the input force, of course, is the force that he applies or puts in, which is, I got 65 pounds. So he puts 65 pounds of force into this thing, and it's a very sticky jack. And it gets 2,500 pounds out of it. And so we simply divide, right? And that gives us the AMA to be
38.46. Yeah.
rounded off to 2 sig figs. And remember, AMA is unitless. The next thing says to find the IMA. Now, I would recommend putting this in the memory because we're going to need it again in a moment. We need the IMA. And we said always, 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 IMA is a ratio of input distance to output distance, right? But for the screw jack, we said the input distance is 2 pi r. And we said the output distance is
1 pitch.
the pitch. And again, we're using very unscientific units here, using inches, but it doesn't matter because they'll cancel anyway. It says the handle's 12 inches long. So if it's a 12-inch handle, that 12 inches is going to be, assuming you hold the handle at the end, is going to be the radius, right? 12-inch handle, assuming you hold it at the end, that's going to be a 12-inch radius, right? So we'll have 2 times pi times the 12-inch radius length of handle. And it says the pitch is 0.18 inches. Obviously, the inches cancel, which just makes it unitless, just as the pounds canceled. And that gives us what for the IMA?
418.87.
Rounded off again to 2 sig figs. 420. So in theory, it should multiply your force by 420 times. But it only multiplies your force by 38 times. That's not particularly efficient, again, because there is so much friction involved. And again, we're very thankful for the friction, though maybe could have gone for a little less. Maybe a little less friction would be nice. You can use that to find the efficiency by taking the ratio of...
Work output. Or wait.
Well, we could do it that way, work output over work input, but we didn't do that. So we would say...
IMA to AMA. Backwards. AMA to IMA.
There we go. What you really get compared to what you thought you would get, right? So AMA over IMA, and then make it a percent, so times 100%. Again, output work over input work should work as well, but we don't know those numbers. I don't feel like finding them. So we'll take the memory value, the 38.4. Oh, probably be good to put this in a memory as well, just to make life a little easier. And then take memory 1 over memory 2. And what do we get for our decimal, first of all?
0.0918.
But move the decimal 2 places and round to just 2 sig figs.
9.2%.
9.2% efficiency. Very low efficiency because of so much friction in the jack. But again, that just means that the vehicle stays jacked up when we take our hand off of the handle. Questions on this problem? How'd we do? Did not do well.
I got about half.
Got half of it.
Yeah.
Questions? All right, clear desk except for a clean sheet of paper and a pencil and a calculator. Clean sheet of paper, pencil, and calculator. And everything else away. First and last name at the top of your paper along with today's date. First and last name along with today's date, which is 12/5/22. 12/5/22 today's date. 522. And this is quiz 14B. Quiz 14B. Let's take a look at the quiz together very quickly. First 6 questions completion. Answers may require more than one word. Write the answer. Numbers 7 through, well, let's say 7 and 8 are separate problems. Then 9 through 12 all connect together. So 7 straightforward, 8 is straightforward, and then 9, 10, 11, 12 all connect. So make sure you hold on to answers, use memories and such. And then there's a bonus for you as well. All right, there will be no homework this evening other than start studying for the test, which will be in 2 more lessons. Lesson 80 will be test 6 over chapters 10 and 11.